So in this lecture, we are going to talk about various optimization strategies that are used to learn a DNN. Now, uh, particularly, gradient descent in its various forms is the backbone of the algorithm behind learning DNN parameters or DNN model. Okay, so we'll basically begin with an introduction and motivation towards gradient descent, and we look at various ingredients that give different flavors of gradient descent, and what are various popular algorithms, popular variants of gradient descent that are being employed in learning DNN models. Now, that's what we like to see. So the general structure of DNN is as follows. Now we denote theta as a collection of parameters at time t plus 1, and theta t is the information that we have about the parameters or the parameters available at time t. Okay. So this g is the gradient of the loss function. If L of theta is basically the loss function, which could be the mean squared loss, it could be a cross entropy, it could be a cosine similarity between these two, difference between the in some sense a function that measures the compatibility between the target and the predicted target. Okay, so g is basically the derivative of the loss function with respect to the parameters. So the general structure is the current update, current state of the parameter is basically theta t minus alpha times g. G is the gradient that basically pushes the theta t in the direction which minimizes the loss function, and alpha is in some sense the step size. Okay, so that's basically roughly speaking the overall idea behind a gradient descent. Okay, for example, in this particular figure, now we have theta is basically a scalar. So we see L of theta as a function of theta. This looks like a ball. So you began with some theta t. You descend in the direction that minimizes the loss function. You get an updated parameter theta t plus 1. You compute the gradient at that particular point at theta t plus 1. You continue further in the direction which leads to the minimum loss function, and you iterate. So at certain time, the difference between theta t plus 1 and theta t is going to be so minuscule that you say algorithm converged. Okay, then generally that's the structure of the update equations. Okay, but what makes this particular thing work? Okay, that's what we're going to see in a moment. So recall that L of theta is basically a function that I like to minimize. In this case, for simplicity, I keep theta as a scalar. So I'm going to approximate this function L of theta so in the neighborhood of theta t using Taylor series expansion. Okay. In particular, I consider the L of theta to be a quadratic function around theta t. So for example, so if you are looking at, let's say, this is L of theta, this is theta t, you're going to approximate this particular function using a quadratic function, okay, using Taylor series expansion. So we know that from first principles, if we like to minimize a function, for example, we consider the critical point of, we take the differentiation and we compute the critical point. Okay. So in particular, if you see L of theta is approximated by the Taylor series expansion involving the second derivative. So this is a quadratic approximation. So we further replace the second derivative with just an identity matrix. In this case, it becomes like a scalar. Okay. So then you're going to see that L of theta is basically L of theta evaluated at theta t. This is the first order derivative of the loss function. So in that sense, basically L of theta is definitely, you see this is a quadratic function because you see this is theta t, this is theta square. This is some function involving theta square. Okay. Now we will take the derivative of the approximated loss function and subject evaluate it at 0, and we'll see what theta do we get. So if I take differentiation with respect to theta t, This is a constant. So so if you differentiate this with respect to theta, you're going to get L dash of theta t, which is the same, and this is 1 plus 1 by 2 alpha times 2 times theta minus theta t, and differentiating with respect to theta is basically 1. So L dash of theta is basically this. If you evaluate the critical point, simply that means that you simply equate this to 0 and see what you get for theta. If you solve this particular function for theta, you're going to get theta is basically theta t minus alpha times L dash of theta. So L dash of theta is nothing but the derivative of the loss function with respect to theta. So that's what you see. Now theta t plus 1 is basically theta t minus alpha times the gradient. That's what we began with. That's the motivation for using this sort of updation equations. That's why it's called as gradient descent. The gradient tells you in which direction to follow. The step size tells you how quickly or how rapidly you want to descend towards minimizing the loss function. Okay. That's basically the fundamental structure against which many variations can be posed. Okay. So what are the various ingredients? Now from an abstract point of view, if you see, theta is basically the theta at time step t. This is the step size. This is basically the gradient. Okay. Then the questions are, now how do you compute this particular gradient? Do you want to compute this on the whole data? Do you want to compute it in a partial? Do you want to consider a smoothed version of it? What could this alpha be? Should this alpha be a constant? Could it be decreasing with diminishing values as a function of time, as a function of progression in time? Should it depend on the second derivatives? So on and so forth. These sort of variation give you different flavors of various optimization techniques. So one of the very popular optimization technique is called as stochastic gradient descent. The motivations are as follows. Remember, in this is our loss function L of theta. N is basically runs from all the way from 1 to n. You are looking at the entire data. So in the gradient descent, we know that we need to compute the gradient of the loss function because this this is summation. You take the differentiation inside the summation. So therefore, the gradient of the loss function is the sum of the gradients of the loss function. So fundamentally, we need to evaluate the loss function at the individual records. So this delta L is evaluated at a particular theta for a given ith record. Okay, and in this case, this is like an estimate of the gradient at time theta t. You see that the loss function gradient of the loss function is an estimate. It's running from all the data points, all the records. So if you for a moment you step out and say that suppose you have a random variable xi whose variance is, let's say, sigma square, and you're trying to learn some function of that sample. It's like a sample mean. If mu hat is basically the sample mean, and we know that the standard deviation of the estimate mu hat is basically sigma by square root of n. So what basically this tells you is that even if you have n samples, the standard deviation, the uncertainty in your estimate goes down by a factor of square root of n. Okay. In other words, if you say that if you collect 100 times more samples, the reduction in the uncertainty is only 10 times. So therefore, you can conclude that the returns are basically sublinear. Okay. If you increase your data size by 10 times, or rather 100 times, then the uncertainty in your estimate is only going to go down 10 times. So you don't get linear returns in terms of reduction in uncertainty. Therefore, we say, then why do we need to base our estimate based on all the n records? Why can't we just take a subsample? Okay, that's the intuition behind coming up with stochastic gradient descent. Instead of taking average of the gradient of the loss function against all the n records, you simply subsample. Okay, let's say you take m random samples of the n records that are available to you and simply compute or simply estimate the gradient of those m samples. That's why it's called as stochastic gradient descent, because now it could vary from one subsample to another subsample. Okay, so why is it helpful? First of all, as we said before, the returns are not linear in the number of records that you have. Therefore, that's one. Second, it sorts of gives you a generalization ability, because you're not seeing the entire data set. It's as if you're cutting your data set into train and test data sets or train and validation sets. It might give you a better generalization. It offers better returns because now you're working with subsamples of the data, and this paradigm is very suitable for big data. You don't need to iterate through all the data sets. You could just work with a few hundreds as opposed to a few billions of records that you have. So by the time you compute one epoch, you might have a pretty good idea about the actual theta that you're caring about, which should minimize your loss function. Okay, so it's very suitable for big data paradigms. That's one motivation, or rather a couple of reasons why stochastic gradient descent is a neat technique. Okay, but as we said before, the plain vanilla stochastic gradient descent uses, let's say, a constant step size. But we know that we could run into problems because you're never going to, the loss is never going to come down, because you're working with random samples. There's always be difference in terms of the gradients. Therefore, it doesn't seem like you're never converging. Okay. So one technique that people often use is to decrease their learning rate as a function of time. Okay. So initially you can begin with large step sizes, but as time progresses, now you could reduce your step size. You make it more smaller and smaller. Okay. So this alpha is basically the learning that controls how quickly do you descend upon. This epsilon naught is basically constant. Now after a while, now you simply say that your ek plus 1 is basically epsilon naught. Epsilon naught is going to be very small, at which point you say that the difference between theta t plus 1 and theta t is going to be pretty small. Okay, so in bottom line, instead of treating the step sizes as small, basically you reduce your step size as a function of time with this particular rule. Okay, that's just SGD with decreasing learning rate. The other variation that one could think of is because you're working with stochastic gradient descent, your estimates of the gradients could be very noisy, right? Instead of computing the gradient on, let's say, all the 100,000 records, you're simply working with, let's say, 100 of them. That means your view into the data set is very partial. Therefore, your gradients could be very noisy. Okay. Then can we not come up with a memory based system wherein your current gradient is also some function of the gradients in the past? Okay, in that sense, basically you're seeing that if the gradient g is basically this current estimate of the gradient, and this v is some sort of a memory. Okay, then your theta is simply going to be a weighted combination of something that's coming from the past versus that is something coming from the present. Okay. So if you notice, for example, the blue line corresponds to a non-smooth version of the gradient. The red line corresponds to a smooth version. Okay, so this could be pretty noisy. A plain vanilla, if you use just the gradient estimate of the gradient computed based on that particular partition, it could be very wiggly and very noisy. Whereas if you use so-called velocity or so-called momentum, which basically smoothes out your rather filters out the gradients based on the past gradients that you have seen, you'll see a lot more smoother descending happening as you are iterating in as you're iterating. Okay, that's a very neat technique one could employ, particularly when someone sees that the gradients are very noisy and so the theta doesn't seem to converge. They could be very noisy. Okay, this is a vanilla momentum update that one could use in conjunction with stochastic gradient descent. So other variation that we could think of on how do you estimate your gradients is by doing a little bit of correction. If this is a vanilla momentum based stochastic gradient descent, now recall that in a vanilla momentum updation, you are evaluating the gradient, or rather you are computing the gradient at theta t, which is what you have seen. But why not we could compute the theta, why not we compute the gradient at the corrected update itself? So instead of computing the gradient at theta t, you compute the gradient at theta t plus alpha v, where now v is basically some sort of filtered or smoothed version of your past gradients. Theta t is basically the current gradients. Okay, so it is something looking like this. So the history is basically encoded by v, theta t is basically what you have seen, and theta t plus 1 is basically the correction step. Okay, in that sense, the current momentum is influenced from the past as well as from the future. So this strictly is basically smoothing. Okay. So once you update, once you compute your estimates theta t, at a future forward step, theta t plus alpha v, and incorporate that in your velocity updation schema, vt plus 1 is some function of the vt and g of t. The gradient is evaluated at a future step, a future theta t that you haven't still observed. As you can see from this equation, this provides a much better smoothing as opposed to the vanilla momentum updates. This is called as a stochastic gradient descent with Nesterov momentum. Okay. Well, so far we have looked at how do we update, how do we compute gradient descents. If you look at the fundamental updation equation, now we are looking at how do we compute the gradients. Okay, first we looked at instead of looking at the whole data, you're going to look at the partial data. Okay, that makes it a stochastic gradient descent. Second, now how do we smooth out our gradient? How do we make sure that the gradients are not very noisy? Okay, even though we happen to consider partial data, by considering historical gradients as well as making few corrections in the future, we don't let g wander completely randomly. Okay, so we still like to reduce the amount of variation that you see in the gradient computations from time to time. So the Nesterov momentum basically attempts to do that. Okay, but we haven't seen how to control this particular alpha. Well, we could recursively reduce the step size. For example, alpha t is alpha t by 2. Okay, but are there better strategies available to control the step size? Okay, that's what we are going to see in the next couple of slides. So the ADA-GRAD basically consider the approximations to the second order derivatives. Okay, for example, this g this is an element wise gradient multiplication. This you can see this is an approximation to the Hessian. Okay, typically a quadratic updations involve Hessian, which is basically the h is basically the second order differentiations of the gradient functions. Obviously, computing the second order gradients is going to be computationally very expensive, particularly if you are working with hundreds of thousands of parameters. So one approximation we could resort to is to approximate h with diagonal elements, and even further approximate saying that my second order differentiations are replaced with square of the first order differentiations. Okay, that's the motivation behind considering. That's the motivation behind ADA-GRAD. Because you have access to the first order gradients, using first order gradients, how do I adapt my step size? Okay, for example, even if you keep your alpha the theta is going to how quickly can you go towards your theta depends on the second order derivatives. Okay, now for example, you can see that Newton-Raphson is basically a certain flavor of this particular function. If the underneath loss function is quadratic, then you get your you in one iteration you reach your you get an optimal solution. So in that sense, you can see that the R basically tries to says how quickly can you accelerate towards your optimal solution. Okay, that's the motivation behind AdaGrad. Instead of using a fixed step size or reducing step size on a certain schedule, you try to learn the rate of learning rate as a function of the gradient themselves. Okay, that's basically AdaGrad. So in RMS prop, it's again slight variation of the AdaGrad. Remember, in the vanilla AdaGrad algorithm, R is basically what you have seen. Okay, so it remembers the entire past. Entire past is basically encoded in R. Okay, and this is basically the present. This is past. This is basically present. Okay, but so if you do a little bit of calculations, you would know that, for example, if you are beginning with R1 is basically, let's say, rho times R0 times 1 minus P times, this is the square of the first order differentiations that you have evaluated at time step T0. Then if you recursively compute your updation equations, you know that your Rn is basically rho to the power of n times R0. So if rho equals to 1, that means the current learning rate or inverse of the learning rate actually completely depends on not completely, but it completely remembers what initial learning rate you began with. Okay, whereas if you choose something like R equals to 0.9, then it rapidly decreases. Okay, in that sense, you can see that the influence of the past exponentially decays as a function of time. That's why it's called as exponentially smoothed out learning rate. Okay, it's a very simple trick, but it works well in practice. But nevertheless, we can come up with more variations. So the RMS prop simply considers exponential decaying learning rate. That's a simple variation what one could think of coming from AdaGrad to RMS prop. That's a variation that you see. Okay, rest of the equations remain the same. Now the immediate reaction to us is, okay, then can we combine Nesterov momentum with RMS prop? Okay, so there is now RMS prop now gives a way of figuring out the learning rate adaptively. Nesterov momentum gives us a smoothed version of the gradients. Now can we combine both? That's exactly the idea behind ADAM. Okay, so you get an updated theta using the existing access to the momentum function. So you see theta tilde is theta plus alpha v. Then you update your computed gradient at the corrected theta. So in a plane in a momentum updation, you compute this gradient at theta itself. But in a Nesterov momentum, you actually consider the correction step for going forward one step in the future, and you're looking at all the thetas, all the gradients looking backwards. That's encoded in V. So you get a updated G. That's your estimate of the current gradient. Then you have you have an exponential decaying learning rate equation. You simply use that to compute your momentum equation, and theta is basically theta plus v. So you're not only you're considering partial data that comes from stochastic gradient descent, wherein the linears are pretty good compared to looking at the entire data set. It works well very well with big data. It provides sort of a generalization ability because you're not seeing the entire data to compute your gradients. Second, But nevertheless, the gradients could be noisy. Therefore, using Nesterov momentum, you estimate the smooth gradients, and you based on the second order approximation, the approximations to the second order, and you approximate the second order gradients and use them to adapt the learning rate, as you would typically do in Newton-Raphson type of algorithms. That gives you an ADAM which combines both RMS prop with the Nesterov momentum. Okay. So as you can see, now ADAM incorporates all the flavors of the techniques that we have seen so far, and ADAM seems to be the default optimization technique that people use in fitting deep learning models. Okay. Um, Nevertheless, to see which algorithm is working, it's always a good idea to look at how basically your training error is basically reducing as a function of time. If you have access to numerical differentiations, plot them, plot the gradients, estimated gradients versus computed gradients. Now, how do they differ? Now, are the gradients changing with respect to time? So based on that, we have to use other strategies such as dropouts. From a modeling point of view, we might need to use skip connections. If you are working with RNNs with LSTMs, you might need to use peepholes. You might need to use some gating mechanisms where the input basically flows directly to the header layer. So if you see sort of issues like vanishing gradients, exploding gradients, you might want to use other techniques like clipping gradients and attack the problem from a different point of view. All right, but nevertheless, ADAM seems to be a good default technique to consider, but we cannot there's nothing like a general purpose recommendation that one could use. It's always a good idea to look at the data, look at the problem, and see whether gradients are working okay or not. Okay, that's about it. Thanks for watching.